Can we get a signal? Do we have a signal? There we go, we got a signal. Hello, it's me again. Doing my stupid shenanigans now on the moon. Gonna be doing something just a wee bit differently today. And hopefully it works out for everybody. And it will feel maybe a tiny bit more like regular teaching. We'll see. All right, and I'm hoping it helps me with my writing and all that sort of stuff, so we'll see how it goes, okay? But today we're talking about solutions and the phase plane, and really what I want to be doing is building up our intuition about why we're doing things the way that we're doing them, and hopefully work through a whole bunch of examples and stuff. So I'm going to be drawing a ton, and we'll see how it goes, okay? But in all of this, we're starting off with linear planar systems. So what I mean by linear is that no x's and y's touch one another. So that the only thing we have in front of x's and y's are numbers. There we go. So in this case, I've got numbers A, B, C, and D. All right, planar is that it's two dimensions, so there's only two state variables, x and y. All right, they're homogeneous. I'm not adding anything to the end of it. And this is just where we start. You know, this is a good place, okay? Now, I think we've done method of elimination before, but we're going to be doing it again and again and again and again. We're just going to show these things over and over again. But I will also argue to do that every two-dimensional linear system can be turned into a second-order differential equation. And I think I'll make a short video doing like a really ugly one, okay? But the method of elimination, as it is called in the book, that's an E, elimination, basically follows by picking one of the equations. It ultimately doesn't matter which one when it's full like this. You want to pick one that's got like probably both variables in it. So I'm going to pick the x equation and take the derivative of it. And I always write plus there when what I need to write is equals. I don't know why I always do that. Ax prime plus by prime. Okay, it's very simple because a and b are both constants. Okay, now this is not good because it has a y in it, but we know what y prime equals from our other equation. So I can write x double prime equals ax prime plus bcx plus bdy. And it still doesn't look like we fixed the problem because we still have a y in there. Well, this is where you take that first equation you started with up there. Wow, it doesn't like writing when I'm actually holding it. There we go. Take this first equation and you can solve it for y. And so what you wind up with is the second order differential equation, like x double prime equals a x prime. I think because it's bouncing. Let me try my knee. This will be interesting. Just relaxing with Professor Warren while we do math. Ax prime plus bcx there we go, plus, now if I look at the first equation here, if I solve for y, I'm going to be dividing everything by b, and there's a b right there in the front. So those two are going to cancel, and what I'm left with is dx prime minus a dx. Okay, I'm going to rearrange all of these terms in group-like terms according to their power of the derivative on x. So I have x double prime minus, good lord, minus a plus d x prime plus ad minus bc x equals 0. Now this is a second order differential equation. It's got constant coefficients, so those guys are numbers, and it's homogeneous. We definitely know how to solve this, okay? It comes down to the characteristic polynomial by basically supposing that x equals e to the lambda t and plugging that in and simplifying to something like this. AD minus BC equals 0. And we solve this for lambda. Basically, we know we can do that. And this is where some of our cases come into play. Okay, so when we end up solving that for lambda, that's what it is. Like the more I have to go away, the more I have to hold it like a paintbrush. Lambda equals a plus d plus or minus the square root of a plus d squared. Did not leave myself enough room there. Minus 4 AD minus BC. And this whole thing is divided by 2. Okay? And now we know we have cases, right? With all these things, we always have at most 2 solutions. In one case, both of my solutions are real numbers and they are not repeated. And in this case, I'm able to write that x of t is c1 e to the lambda 1 t plus c2 e to the lambda 2 t, where lambda 1 and lambda 2 come from the plus or minus, right? If I have a repeated real root, that was a special case. And what we worked it out is that it could be c1 e to the lambda 1 t plus c2 t e to the lambda 1 t. And again, here I wrote lambda 1 twice because lambda 1 equals lambda 2, because basically, in that case, everything under the square root there would have to be 0. Okay. We also had the complex root case. All right, and this one was a lot of work, but it ended up being, I think, fairly straightforward. It was just a lot of doing. All right, but we have c1 e to the alpha t cosine beta t plus c2 e to the alpha t sine beta t. And this alpha and beta come from the fact that our lambdas here would equal alpha plus or minus beta I once we simplified some stuff, our complex roots. Okay, and this is nice. So great. What does this mean? I can start with any system I want, like this guy up here. Okay, I can use the method of elimination and write it as a second order differential equation. Then through characteristic polynomial, I can come up with a solution and we'd be done, right? Like this is fine. But here's the thing. What are these 3 guys? They're all solutions to x. Okay, what about y? All right, that is a little trickier. Okay, so if I just rewrite the system real quick, it doesn't like it when I write quick, so I got to write slow. X prime equals ax plus by, and y prime equals cx plus dy. Now we suppose we know know x. Okay, now if b doesn't equal 0, well then since I know x, I also know x prime. And so then I would know y is x prime minus ax all over b. I would know y. Hooray. Right? If b is 0, I can't use that first equation. Okay? But then what that means is my system is partially decoupled. Because basically, if b equals 0, then this whole term is gone. And we can see that x only depends on its own value. So since we solved that basically all by itself, we'd be able to plug in our solution, x of t, into y prime equals cx plus dy, and then solve that through whatever method. You know, presumably then right here we've got some function of time, and so then that's not divide. This right here would be, there we go, some function of time, and then we would use integrating factors or something to that effect to get at what we need. Okay, and so that's fine. Okay, that's fine and dandy. And ultimately, like what this gives you is it gives you x and y as functions of time, right? So let's just kind of like go over like a few maybes, right? So here's my x, here's my y. All right, first color in the docket is orange because I'm not using yellow anymore because it's a garbage color. All right, maybe we get that x is an exponentially growing function, you know, and y is also exponentially growing. Like that's a possibility, right? We could get that x is growing, oh, but y is shrinking, right? Oh, we have complex values. So x could be oscillating. Oh, and if x oscillates, y also has to oscillate, right? Because then we'd have all these sines and cosines. You can't just have it one way and not in the other. Maybe what else one I got? Oh yeah, x could be shrinking and y could be shrinking at the same time. And these are nice. These are 4 different equations. We have the orange equation, the red equation, the magenta equation, and the green equation. Okay, and all sorts of different scenarios of what they could be. But if we look back at our system, right, it's not like you were talking about the motion of a weight on the end of a spring and watching it go back and forth. And so then all you're really concerned about is the location of that weight, right? That's not from the modeling perspective where we started with. If I wrote down a second order differential equation right off the bat, that would be the modeling perspective. Like, here's a thing, and I want to know how that thing evolves over time. Here I've got 2 dudes, right? I've got x and I've got y. I've got 2 equations. And so really what I'm talking about is x and y influencing one another. And that seems to be the real target here. While these 2 things, these graphs I've drawn, are not incorrect, it may not be the point that I'm after. So instead, I may be interested in what's going on in the xy plane. All right, this is called the phase plane, usually. All right, and I can couple these with our solutions here. So in this one, x and y were both growing, right? So maybe my solution looks something like this. And then depending on where I start, in either case, they are growing away from 0, right? The next color we've got is red. So in the red situation, x was growing. Oh, but y is shrinking. So I'm going to be moving horizontally away from the vertical axis, right? But y is shrinking, so I'm going to be moving toward the horizontal axis like this. All right, so I'm probably going to look something like that. All right, this graph's going to get messy. Deal with it. All right. In the magenta case, we have oscillations, so I probably have some sort of ellipse, some elliptical path that we're spinning around, right? And then I guess the last one we've got is the green equation where they're both decaying. It probably looks something like this as they head on toward the origin. All right. Now, what I'd like to do is to build for us where all this comes from and how we actually can do it without trying to guess, like how we know these things are the pictures that I want to draw or the whatnot. Okay. It's important to keep in mind that all of this comes from lambda equaling a plus d plus or minus the square root of a plus d squared minus 4ad minus bc all over 2, right? These are those exponents that really determine what kind of solutions do we have. Are they growing? Are they shrinking? Are they oscillating? Et cetera, et cetera, et cetera. Now, since we are thinking a lot in the xy plane, it may be useful for us to, instead of thinking these things as 2 separate equations, to really formulate it as a single entity. All right. So let's go ahead and define a vector u, which will have elements x and y. Draw the y. There we go. And I'm going to let a coefficient matrix A be A, B, C, D. And so I can rewrite that system of differential equations as sort of a single vector value differential equation. It doesn't really change it at all. It's just putting us into a particular frame of mind. Okay. Now, what's really interesting here is that we have all these quantities up here that have to do with various elements of the matrix, and some of them actually have special names. Actually, they all do in this case. But we're going to go ahead and let tau, this Greek letter tau, be the trace of A. And what the trace is if you take all the elements along the diagonal and you add them up, that gives you the trace. So this is A plus D. That's just a property, a certain metric of matrices that is standardized. And we're going to let capital delta be the determinant of A. And what the determinant of A is, if you multiply the 2 fellas on the diagonal and then subtract from that, at least in the 2 by 2 case, the two fellas that are not on the diagonal, their product, you get AD minus BC. And so in this case, just to sort of phrase this in terms of dealing with matrices, lambda is equal to the trace plus or minus the square root of the trace squared minus 4 delta all over 2. So now we have properties of the matrix. Because where did our lambdas come from previously? We had to do the following. Take our system, use method of elimination to write down a second order, write down the characteristic polynomial, then find the roots of the characteristic polynomial. That's how we had to find lambda. So now, at the very least, as a nice little shortcut, write it in vector form, and then when you got your coefficient matrix, you compute its trace and its determinant, and then la-di-da, they're your eigenvalues. Okay, those are your lambdas there. Yeah, I think, we're going to continue on with this video here. It's a little bit of a long one, but that's okay. That's setting the stage there for thinking about things in a planar sense. What I want to do is motivate you guys for why straight line solutions. I don't think I gave a really good, like, hey, why do we care about these things called straight line solutions? Okay, and I really want to build up just a couple different ways of thinking about it. Okay, like why this is a thing that we're looking at. So we have an algebraic way of thinking here, and what this has to do is basically all matrices of this form, A, B, C, D. There we go. Can I write that? Thank you. Have eigenvalues. Okay, if you don't know what an eigenvalue is, that's fine. If you do, keep that in mind. And when I say they all have eigenvalues, they can be real valued and distinct, they can be repeated real values, or they can be complex. And that's what allows us to say all of them, right? You know, like they might be real, might have 2 real, we might have 1 real, or they might be complex. And all of these are fine. Okay, and so we can find a number lambda and a vector or direction v such that when I take A and I apply it to V, it is the exact same as taking that number and applying it to V. And so this transformation A in this direction V behaves exactly like scaling. I know we've kind of talked about this, but you know. And so, and what I'm about to write is very ishy, like it's not precise here. But so if I write my planar system like this, vector valued, okay, this is in some sense very similar to x prime equals lambda x. Okay, this is not perfect. Okay, it's a good way of thinking, I think. And so when we're manipulating it, we've got these numbers, and we know how to solve equations that look like just a number times that, right? We know how to do that. You know, from there we just get exponential growth or exponential decay. Like we understand those. Okay, and so because these things are two-dimensional, we can find 2 of these lambdas and 2 of these v's. And so we've got 2. Don't mean to put a C1 there. That C1 should not be there. We've got 2 solutions like x1 of t, which is that vector, e to the lambda 1t, and x2 of t, which is the other eigenvector that corresponds to the other eigenvalue. Here, I'm kind of ignoring the case of repeated eigenvalues. We'll get there. I bet you can guess what you have to do. It involves a t. All right. But so basically, we can find 2 separate solutions. And since v1 and v2, these eigenvectors, since by construction they're independent from one another, that means these solutions are independent from one another. And so I can write a general solution as c1 x1 of t, plus c2x2 of t. And I have, let me write it like this. And then you have a general solution for your equations. And so these guys right here, this is sort of our motivation for looking at straight line solutions algebraically. If I think geometrically, metrically. Cool. That's easy to say, easy to spell, really hard to write, apparently. All right, let's take a couple scenarios here. Let's say that x experiences exponential decay. Okay? Can you guys hear that? Oh my god. So in either event, it decays to 0, whether your initial condition is positive or negative, right? And let's go ahead and say y, conversely, experiences exponential growth. Okay? So if I think about this, and these guys are coupled within some sort of system, x is always going to 0, y is always blowing up. So it looks something like this, right? Where I'm always moving to the left and up. And over here, I'm moving to the right and up. And over here, I'm moving to the right and down. And over here, I'm moving to the left and down. Okay? Now, what's important here is that in between these curves, one of my variables always changes direction. Like between this top half and the bottom half, I change from going up to going down. So there has to be a solution in there somewhere that goes neither up nor down. When I change from the left-hand side here to the right-hand side, I need another color, there we go. The right-hand side here, I change from going to the right to going to the left. So there has to be a solution somewhere in the middle there that goes neither right nor left. And in fact, like these things are made precise, and we will continue to make them precise as we move through the lecture. Go away, yeah. We have a pure up and down solution right there that just goes away from 0. And we have a pure left and right solution that goes towards 0. All right, and so geometrically, like those things should exist. So we should be looking for straight line solutions in the plane. All right. Another place to get, I don't know, some intuition from is from differential equations directly. A differential equation gut check is what I can call this. All right. And we think about this with the simplest differential equation I asked us to solve that wasn't a calculus problem, right? X prime equals ax. The solution to this, x of t, was the initial condition e to the at. And functions like this have served as the fundamental building blocks for all of our solutions. Sure, when we have non-homogeneous terms like some f of t added on there, things get more complicated. But ultimately, when we're just looking at the core differential equation part right there, our solutions look like exponentials. And so if I'm writing this vector valued problem, then when I think about my solution, it also needs to be a vector, right? And so if I just want to think about a number times e to another number t, the problem is here, this is not a vector. So there has to be some vector in here that makes it work. Now the other thing is, this is 2-dimensional, where this is 1-dimensional. So I know I need 2 degrees of freedom here. Here's one of them. Here's my other one. And so I should be looking for another piece of the puzzle that looks like that. And that should motivate us on why we're looking for exponential functions. Okay. That's it. That was long. Thanks for sticking through it. My baby was crying, but my wife's with her. So everything should be okay. I'll see you guys soon in some other videos. Okay. Where's the recording stuff?